Students, we will continue with the chapter of center of mass. This class will try to finish these topics: center of mass, conservation of momentum in system of particles, center of mass of a uniform rod, moment of inertia, radius of gyration, then the parallel axis and perpendicular axis theorem, and some of the examples in which case you should know to find the moment of inertia, or you should know the formulas. We will not go into the details of the derivations because of the shortage of time. So, in the last class, if you go back to the topic that we discussed of center of mass, we defined the center of mass of two bodies M1 and M2. M1 is at R1 position vector, M2 is at R2. The center of mass is capital RCM, and these are the formulas that we found out. This is the definition: RCM will be equal to M1 R1 plus M2 R2 divided by M1 plus M2. VCM M1 V1 plus M2 V2 by M1 plus M2, and SCM is M1 A1 plus M2 A2 by M1 plus M2, where V1 V2 are the velocities of the individual particles, corresponding particles. A1 A2 are the individual accelerations. For example, A1 is the acceleration of M1, A2 is the acceleration of M2, and so on. So, the total mass of this system is M1 plus M2. So, I can in this case I can replace it by capital M. Now, we also found out that the total force on the system will be equal to, simply if you add up all the forces, you get this as the only the external forces. The internal forces cancel out, and what we get is the external force, and this external force will be equal to mass into mass. The total mass is M1 plus M2 into ACM, or if I write in this place, if I write M, then I write it as M ACM. Now, if our external force is 0, total external force acting on the system is 0, then what we find that on the right hand side mass cannot be 0. So, what remains is ACM is to be 0. That means acceleration of the center of mass is 0. Now, what is acceleration of center of mass? Acceleration of center of mass is this, and this is equal to the derivative of time derivative of VCM. So, this is 0. If the time derivative of a quantity is 0, that means that quantity is constant. So, this gives me VCM is constant. Force can also be written as, or from this also you can say, if this is constant, because M is constant, I will multiply with M into VCM, this will be constant. Now, mass, total mass into the center of velocity of the center of mass, this gives me momentum of the system. This is nothing but the momentum of the system, total momentum of the system. Total momentum is equal to your this M VCM. So, the total momentum of the system is constant. So, this is our conservation of linear momentum for a system of particles, that when there is no external force on the system, no external force, the total momentum is constant. Each individual particle may have some velocity, but the changing velocities, each one may have A1 and A2, accelerations are there, but ACM is 0. That means, if A1 is in one direction, A2 has to be in the opposite direction. Second thing, ACM is 0, When external force is 0, acceleration of center of mass is 0, velocity of the center of mass is constant, momentum of the center of mass or total momentum, this is nothing but the total momentum of the system, that is constant. So, this is our conservation of linear momentum, this is nothing but our conservation law. So, next we will calculate the center of mass of a uniform rod. Now, not only a rod, any uniformly distributed mass, if you have a body with uniformly distributed mass, then the center of mass will be its geometrical center. Remember this. So, it will be this is a general geometrical center. How do I get this? Let us take a uniform rod. Let us say this is my origin, this point is the origin O0, and I will take a small mass which is a small section of this rod at a distance x. I will take a dx length, this length is dx length of the rod. Now, for that I should give you, this is the case of individual particles. But when the particle is continuous, that means particle not continuous, but the body is a continuous body, means it consists of particles which are continuously present in the body. For example, these particles are not distributed individually or discrete, it is a continuous mass. For example, this is also a continuous mass. For a continuous mass body, our center of mass definition will be 1 by total mass, just as here, into, now here m1 into r1. So, r into the small mass and you integrate it over the entire body. This will be the center of mass of a body when it is a continuous distribution of mass. If the mass is continuously distributed, then that is the definition of your center of mass. So, I will use that. At the distance of x, there is a small length of the rod dx. So, the mass of this dx length, the mass of that thing, mass of it, which I write it as dm, the small mass, this is equal to, let us say the length of this rod is L and the mass of this rod is, total mass is capital M. Then if L length has a mass m, unit length will have, L length has mass m, 1 centimeter or 1 unit length of mass will be m by L. So, this is unit length of mass. Now, this body has a length of dx. So, the mass will be this, mass per unit length into the length will give you the mass of that small elementary length dx. So, this is dm, it is placed at the position x, and since it is a one dimensional body and it is placed along x axis, I am saying, then the center of mass will be somewhere on the x axis also. So, it obviously center of mass, that means I should give it RCM. So, the center of mass will be, that means only the x component is there, because it is one dimensional and it is along the x axis. So, the RCM will be on the x axis, not on y or z, there is no variation. So, XCM, RCM jagare mu XCM lekhili, because it is on the x axis only. I understand that it will be I cap times XCM. So, this is equal to 1 by m r. Where is it present? It is present at x. I am taking the magnitude only, considering that this is in x axis, this is also in x axis, into dm. So, dm is equal to here 1 by m x times dm is m by L dx, and to be integrated from 0 to L. Dx is the variation of x starts from 0 up to L. So, I am integrating it 0 to L, it will cover the entire body. So, this equals to m cancels out. So, 1 by L you have x dx from 0 to L. Now, this integration is 1 by L x square by 2, and the integration is from 0 to L. If I put this value, it is 1 by L square by 2, this comes out to be L by 2. So, the center of mass is on the x axis at a distance L by 2. I have told you already that because the mass is uniformly distributed, it will be on the geometrical center, and the geometrical center of this rod is halfway L by 2. So, this is what we got in for the center of mass of a rod. So, we move over to another topic of moment of inertia, which is very important in reading the system of particles or rigid body, and especially the rotation of a rigid body. Now, when I say inertia and moment of inertia, now inertia you have read in your Newton's laws chapter. The first law gives you the definition of inertia. What do I mean by inertia? In linear motion, inertia is the property by virtue of which a body continues to be in the state of rest or uniform motion unless until a force is acted upon it. That means, a body has an inherent property. If it is at rest, it wants to remain at rest. It will continue to do so unless there is an external force on it. If it is moving in uniform motion, then it will continue to do so unless there is an external force. So, this inherent property of continuing in its own state is called inertia. That is, in linear motion we call it inertia. Something like if you have a holidays, छुट्टी अच्छी छुट्टी रे मजा करूच, पढ़ा पढ़ी किछि नाही किछि आराम रे बुलुच. So, when the college reopens, कॉलेज को जीवा को हेला बेले आउ इच्छा हुए नहीं जीवा पाई. So, that means you are in a state of inertia of मजा करिवा खेल बुलिवा यही सब अच्छा. You are continuing your state, you don't want to change your state. So, this is what is inertia. जो भावरे अच्छा तो you want to continue in that state. So, if every body has that inherent property to continue in the state of rest or continue in the state of uniform motion. If you want to change that, गोटे धरा जाऊ गोटे स्टोन टे रखाई गोटे पत्थर पड़ी ताको जदि किछि फोर्स न दिया जीवो से काला काला धरी सेठी पड़िथिवो काहेकि ना तार इनहेरेंट प्रॉपर्टी अछि जे मु एठी अछि मु एठी थिबी मु कुआडे जीविनी आपे आपे जीव आई परिवनी से. So, this is the property of inertia, that a body can opposes, it has an inability to change its state without a force. Now, similarly in the rotational motion, the same property, inherent property is called moment of inertia. So, moment of inertia is an inherent property. Inherent माने ता भीतर अछि ताको कुआडो बाहरु केही देई नांती. Inherent ता निज भीतर रो गुण सेटा. Inherent property of a body by virtue of which it opposes any change in its rotational motion unless a torque is applied on it, actually, because rotational motion is caused by a torque that will come. A force creates the linear acceleration. Similarly, to rotate a body you require a torque, moment of a force. So, the inherent property of a body by which it cannot change its rotational motion. If it is rotating with certain velocity, it continues to do so unless somebody else, something else, that is torque, applies on it. So, moment of inertia unlike the inertia, what is the moment measurement of inertia in linear motion? That also you have read, that inertia, if I go to inertia of linear motion, this is in linear motion. Mass is the measurement of inertia, because a body which has more mass opposes more. धर गोटे बड़ पत्थर अच्छे गोटे छोट पत्थर अच्छे क्या आम इजिली बाहर घुंचे दे पार बड़ पत्थर को घुंचाई आमको बेसी फोर्स दरकार छोट पत्थर को घुंचाई आमको कम फोर्स हेल्ले चलीज घुंचे दे पार सो तार अपोजिशन ताने कम अच्छी जी छोट मास तार अपोजिशन कम है मुझे फोर्स अप्लाई कली इट इज अपोजिंग लेस सो इट्स इनर्शिया इज लेस व्हेयरएज ए बिग मास अपोजेस मोर मत से बेसी फोर्स दबाक पड़ला सो दैट इज व्हाई तार अपोजिशन बेसी अच्छी and that is why its inertia is more. So, mass is a measurement of inertia in linear motion. In similarly, moment of inertia is measured by, see moment of inertia, for example, let us take the case of a गोटे छोट पिलार गोटे साइकिल नहीं करी से जाउची बाटरे गोटे धर एठी गोटे पत्थर आसिला से पत्थर आसिला जेमती ये साइकिल गड़े की नहीं की जाउची रास्ता रे पत्थर टिके आसिला जेमती रही जाउची से. Whereas, if you have a truck, suppose this is a big wheel with more mass and more mass is distributed here. So, if this is a truck and it goes and there is a small stone like this, it goes over it. ता ऊपर को चढ़ी करी से सेमती पड़ेला एमती हेकरी से पड़ेला. So, which has more moment of inertia? Which has more? That means, if somebody continues in its state, तारा inertia बेसी, moment of inertia बेसी. But ताकू जदि change कर दे पारला, बाहर external agent ताकू change कर दे पारला, तबे तारा inertia टा कम. So, moment of inertia भी सेया for a rotating body. एठी a cycle case रे it stops here. The cycle wheel stops here. That means ताको अपोजिशन टिके दो दो टिके छोटिया पत्थर खंडे आसला बेल को से रही जाउची तामान तार जो रोटेशनल मोशन दिस वाज रोटेटिंग दे वर ऑल रोटेटिंग सो रोटेशनल मोशन कुड बी चेंज्ड बाय ए स्मॉल स्टोन द reaction or the opposition of given by the small stone could stop this cycle's wheel ता माने तार कम अपोजिशन थिला ता माने तार मोमेंट ऑफ इनर्शिया कम. Whereas a truck wheel has more moment of inertia and that is why it continues its state. ताको opposition है परलानी. It continues it तारा property of continuation चलिला से rotate है पड़ेला. That means its moment of inertia is more. So here the moment of inertia is more. So if you can change it, moment of inertia is less. If you cannot change it, external agency cannot change it, say continue kalata motion, then its moment of inertia is large. But how do we measure and how do we calculate all these things that we will read. So, moment of inertia depends on the distribution of mass. This not only depends on the individual mass of the bodies, but distribution of mass. This is more important. How the mass is distributed, distribution of mass about the axis of rotation. For example, you have a ring. गोटे रिंग रे सबू मास गुड़ाक पतला रिंग टे मुझे बड़ चौड़ा करदेली एटा को दिस इज ए रिंग लेट्स से इट्स मास इज m एंड यू हैव ए डिस्क डिस्क माने मास सबुआड़े अच्छी भितर भी अच्छी तार भी मास m दिस इज माय डिस्क दिस इज ए रिंग बोथ हैव सेम मास बट यू विल सी दैट द मोमेंट ऑफ इनर्शिया ऑफ द डिस्क इज लेस भितर मास अच्छी तार सबुआड़े मास तामाने डिस्ट्रीब्यूटेड होगी अच्छी एटी कहीं कमिला ना एटी कौन है सबू मास गुड़ाक सबू समस्ते आर डिस्टेंस अच्छा दूर रे अच्छा यहाँ यही चारिपटे बुलिबो दिस इज माय एक्सिस ऑफ रोटेशन दिस बॉडी विल रोटेट अबाउट एन एक्सिस परपेंडिकुलर टू द प्लेन ऑफ दैट बॉडी सो इट विल रोटेट अलोंग अबाउट दिस एक्सिस ऑल द मास दिस मास इज एट आर डिस्टेंस this mass is at r distance this mass is also at r distance. So, all of them at r distance. So, they are away from this center of rotation. Whereas, in this case, if this is my axis of rotation, you see that this mass, if I take mass here, is at a smaller distance. This mass here is at a larger distance. So, यार moment of inertia कम हबो. So, each particle जदि moment of inertia को हमें मिसेइबा, जो माने भीतर अछंती तांका moment of inertia कमी गला, and that is why disk will have less moment of inertia than the case of ring. That we will also find out. So, moment of inertia depends on the distribution of mass, how mass is distributed about the axis of rotation. When I say axis of rotation, when a body rotates, for a rotating body, for example, if I take a rigid body, when it rotates, suppose about some line it rotates, this line or this axis may be inside the body or may be outside the body. Each mass of this body moves in a circular motion, each mass, this mass moves in a circle. If I take a mass here, it will also move in another circle. Center of this is, let us say this C2, center of this is C1, and if I take this mass, it is also rotating about center C3. If this is, these are the three masses I have considered. All these centers, the axis passes through all these centers. So, that is called our axis of rotation. Axis of rotation contains the center of rotation of each individual masses. So, it is perpendicular to these planes of rotation of these masses. So, axis of rotation is that. In case of a ring ro mass ta bahar pate achi kebala. The axis of rotation here I can take that center of the ring perpendicular to the ring. Then I will say this is my axis of rotation. If it rotates about that, then it is the axis of rotation. The axis of rotation here does not pass through the body. So, axis of rotation meaning hela ya. So, the moment of inertia of a body, rigid body, how, but before that let me give the moment of inertia of a simple any one body, point mass of a mass. Let us say there is a mass which is rotating about this axis. This is the axis of rotation and this is the mass. Then the perpendicular distance, take the perpendicular distance, if this is r, then the moment of inertia is m r square. So, with the help of this, we will write the formula for the moment of inertia of a rigid body. So, let us say this is my rigid body and this is the axis of rotation. Let me take it as z dash. I will consider that the rigid body consists of several masses, and these masses, let us say this is m1 which is at a distance of r1 from the axis of rotation. This distance is perpendicular distance. So, if all these distances are, that means from the center of rotation, this m2 will move in a circle around this axis of rotation, the center is here. So, this distance is r2 and so on. If this is my nth mass and it is at a distance of rn, this is m3 is at a distance of r3, then the moment of inertia of m1 is m1 r1 square. Moment of inertia about axis z dash. This is for the first body, and for the second body it is m2 r2 square. So, I will add them up, m2 r2 square, then for the third body it is m3 r3 square and so on. for the nth mass, this will be mn Rn square. So, this is our moment of inertia of a rigid body. Now, I have taken it as a individual discrete masses, but in most cases it is a continuous distribution of mass. So, we will have to convert it into an integral. So, when I convert it into an integral, this will be equal to dm r square. So, you must integrate it over the entire mass. Then another definition is radius of gyration. For example, let me take the case of example of a ring. Let us say this ring has a mass m, it has no mass inside, only on the rim, on this side, on its rim all the entire mass is distributed on its rim, and let us say its mass is m, the radius is r, and the axis of rotation is perpendicular to this. So, axis is passing through this axis perpendicular to its plane through O. This is the axis about which the ring is rotating. Now, let me take a small mass delta m, it is at a distance r, another m, it is also at a distance of r, another m, that is also at a distance of r, then the moment of inertia will be m r square plus m r square plus in this manner for the entire ring. So, if I take r square out and all the masses are added up, that is nothing but the total mass, this is nothing but total mass. So, for a ring, the moment of inertia about an axis passing through its center and perpendicular to its plane is m r square. See, be careful, if the axis of rotation changes, then the moment of inertia will change, because we are taking the distances are measured from the axis of rotation. If you change the axis of rotation, the moment of inertia, these distances will change, and hence moment of inertia is not a not only constant particular value. If you change the axis of rotation about which the body is to be rotated, then the moment of inertia will change. So, be careful, you must specify what is the axis of rotation, about which axis the body is moving or rotating, then only you can say that this is the moment of inertia about that axis. So, moment of inertia about the center and perpendicular to its plane about this z, about the axis that I have defined here, z dash is this m r square. This is the case of a ring. Moment of inertia of a ring about its center passing and perpendicular to its plane is m r square. Radius of gyration. In the study of rotating body, many times we talk about radius of gyration. Now, to define radius of gyration, let us say this is my rigid body, this is the axis of rotation, z dash is the axis of rotation. Let us say this mass has a mass, this body has a mass m, and the moment of inertia of the body about this axis that I have shown about z dash is I, let us say. Some formula, something you calculate and you find that the moment of inertia is I. Now, let us forget about the entire body. I say that there is a mass, I will keep this mass, I take a point mass whose mass is m. And total mass ta ko mu gote jagare rakhili at a distance of k from the axis. Now, we have studied that for a single mass, if from the axis of rotation distance is r, then the moment of inertia is m r square. Now, I have kept the entire mass m as a point body, not as a rigid body, but as a point body and keep it at a distance of k. Then the moment of inertia about that same axis will be m k square. So, if I take this point mass, the moment of inertia of this point mass of inertia of point mass of the same mass value, point mass about the same axis z z dash is m k square. Connection is this, that if your m k square is equal to I, then k is called radius of gyration. In the case of ring, about the center m r square, ता माने एटा समान हबो जदि मु सेंटर रु r डिस्टेंस रे गोटे पॉइंट मास कैपिटल m रखिबी, तेबे तार पॉइंट ऑफ अबाउट दिस एक्सिस द मोमेंट ऑफ इनर्शिया विल बी इक्वल, देन देयर k is equal to r. So you can write it in your own words. It is the distance from the axis of rotation, where if the entire mass is kept as a point mass, the moment of inertia of that point mass will be equal to the moment of inertia of the whole body about the same axis. So you write it that way, that is the radius of gyration. Then the come to parallel axis theorem, because these two theorems will help you in calculating the moment of inertia about different axes. If you know some parallel axis or perpendicular axis formulas, so the parallel axis theorem. Similarly, as it says about parallel axis, means there must be some two axes which are parallel. The moment of inertia of a body about an arbitrary axis is equal to the sum of moment of inertia of the body about an axis parallel to it and passing through the center of mass So, if this is an arbitrary axis, let us say x dash, or let me write p q, you want to find out the moment of inertia about p q is equal to the sum of moment of inertia of the body about an axis parallel to it. ता माने p q को parallel. Let us say this is z z dash is parallel to p q, z z dash is parallel to p q, and the center of mass, it passes through the center of mass of the body. So, and center of mass is on z z dash. These are the two conditions that must be satisfied. Then the moment of inertia of the body about an arbitrary axis is equal to the moment of inertia of the body about an axis passing through the center of mass, and this axis must be parallel to this arbitrary axis, plus sum of, सेथिमाई लिखली sum of through the CM and mh square or and mh square, where m is the mass of the body and h is the separation between the two axes. Here my two axes are p q and z z dash. The separation between them is h, and the mass of this entire body is m. Then it says that moment of inertia about PQ is equal to moment of inertia about through the center of mass if the axis passes through center of mass, and this axis must be parallel to this, plus mh square. If h is the separation between the two axes, then this z z dash is parallel. Here my z z dash is parallel to PQ, z z dash passes through CM, center of mass, and h is separation between the distance between perpendicular distance, separation between my z z dash and PQ. Then, so that means if you know the moment of inertia about an axis passing through the center of mass, then you can find out moment of inertia of the body about another axis which is parallel to that or first axis by applying this parallel axis theorem. For example, we have found out the moment of inertia of the ring about an axis. This is the center of mass. So, this is my ring and my z z dash here is passing through the center of mass. This is the center of mass. So, moment of inertia of ring about the center of mass is equal to m r square, that we have found out, if m is the mass of this ring. I want to find out moment of inertia about an axis parallel to this z z dash. Tamane more PQ is now, this is z z dash, this is P and Q, where these two axes are parallel to each other. Let us apply the parallel axis theorem. It says that moment of inertia about PQ will be equal to, so this is tangential. So, this is an axis which is tangential to the ring, perpendicular to its plane. So, तामने ताकु टच करिके ring टा एमती अछि, ताकु टच करिके एमती जाइछि. So, is equal to moment of inertia about the center of mass. Now, moment of inertia about the center of mass is m r square. So, m r square plus a mass of the body into separation ro square. Eti more h value is equal to r. So, this plus m r square. So, this gives you 2 m r square. So, if you know the moment of inertia of the ring about its about an axis passing through its center and perpendicular to its plane, then you have found out the moment of inertia of the ring about a tangential axis parallel to that earlier axis. So, is 2 m r square. So, ethi jodi axis ta jodi PQ hoji, then the moment of inertia will become 2 m r square, not m r square. So, be careful, axis of rotation change hele moment of inertia will change, and this is how you apply the parallel axis theorem. The second axis, the axis about which you are finding out must be parallel to the axis passing through the center of mass. Add m into h square, h is the separation. Then come to the perpendicular axis theorem. Now, parallel axis theorem is applicable for the 3-dimensional case. For you, we will take the perpendicular axis theorem for a lamina, which is a 2-dimensional body. We take the 2-dimensional or a 2-dimensional rigid body. This is equal, that means I will have a lamina. A lamina is any shape, flat gote patala bhava plate gote, je konasi gote shape ra irregular shape ra plate. Tamane it is in 2 dimension, it has some area, it has, you can measure it, give 2 axes, x axis and y axis, je konasi duita perpendicular axis ku x axis y axis koi dei pariba, and it lies on that axis, on that plane. Now, the moment of, as the name indicates, it is perpendicular axis, tamane there must be something perpendicular. So, if you want to find out the moment of inertia, the moment of inertia of a body now let us take it this way. Describe kariya purbaru, let me take, and this is an axis z z dash, is the axis passing through the center of mass. This is my center of mass, and z dash is perpendicular to plane of the lamina. खाली सेंटर ऑफ मास नहले भी चलिबो थ्रू एनी पॉइंट. मोमेंट ऑफ इनर्शिया धरा जाओ एटा तुम जानिच. इट सेज दैट द परपेंडिकुलर एक्सिस थ्योरम सेज दैट द मोमेंट ऑफ इनर्शिया ऑफ ए बॉडी अबाउट मोमेंट ऑफ इनर्शिया of a body about an axis perpendicular to its plane is equal to the sum of moment of inertia of the body about two axes to mutually perpendicular axis lying on the plane of the body which intersect at a point through which the perpendicular axis passes. That means z dash is first thing, z dash is perpendicular to the plane of the lamina. This is my lamina. I will choose any two axes lying on the surface of the lamina, let us say this axis and perpendicular to that. So, these are the two axes, let me say this as x dash and y dash. X dash perpendicular to y dash lying on lamina. लामिना ऊपर अच्छी ता माने तीन टा का एक्सिस x डैश y डैश और z डैश परपेंडिकुलर टू इच अदर. तीन टा जाक म्यूचुअली परपेंडिकुलर हो गले. एमाने दीज आर नॉट फिक्स्ड. एटा एमती भी हो पारे, एमती भी हो पारे. ता माने एमती जो अछंती एमती जगह अछि आई कैन टेक एनी अदर एक्सिस ऑन द प्लेन ऑफ द लामिना. सो x डैश y डैश आर ऑन द लामिना. They are lying on the lamina. They are perpendicular to each other. So, जदि z dash तांका plane को perpendicular ता माने से माने perpendicular to z dash also. Then it says the moment of inertia about z dash of the body, and another thing, these x dash and y dash intersect at a point O through which z dash passes. So, x dash intersect y dash at O and my z dash passes through O. These are the conditions. Then moment of inertia about z dash is moment of inertia about x dash and moment of inertia about y dash. Or we simply write it as Iz can be written as Ix plus Iy. These two are axes on the plane of the lamina. This is the axis perpendicular to the lamina, and all these three axes intersect at one point on the lamina equal, which is O here. So, you can apply, for example, in the case of ring. Let us take the example of the ring again. In the case of ring, the moment of inertia about an axis perpendicular to its plane, I have said mr square. Even though it is it lies on the ring can be thought to be lying on a plane. on this plane. I will choose any two axes, that means I will choose this line and a line perpendicular to it, and I call them, they are my axis. Then this is x, let us say this is my y. तार गोटे axis, एटा गोटे axis. So moment of inertia about any diameter. This is one diameter, this is also another diameter. Now both these moment of inertia will be same. There is no reason why moment of inertia about another one diameter is different from other diameter. It is symmetrical about that line. So that is why the moment of inertia about this axis, let us say, is Ix. Moment of inertia about this axis is Iy, and the moment of inertia about this is Iz, which we have already calculated mr square. So now I am saying that Ix will be equal to Iy, because both of them are identical axes. So that is why Ix is equal to Iy. The perpendicular axis theorem says that Iz, which z axis is perpendicular to the plane of the lamina or the plane of the ring, equals to Ix about x axis and about y axis, the two axes which are perpendicular to each other lying on the plane of the ring. Then Ix is equal to Iy, tamane eta equal to Ix, tamane 2Ix or 2Iy, tamane Ix is equal to Iz by 2, which is also equal to Iy. Tamane my I over x about x or I about y, any diameter, is Iz is mr square. So mr square by 2. So about these two axes, moment of inertia will be equal to half mr square. Epotre half mr square, eita madhya half mr square. So moment of inertia of the ring through about an axis perpendicular to its plane passing through its center is mr square. About tangential axis हमें बाहर कले by parallel axis theorem is 2 mr square. Moment of inertia about a diameter, I about a diameter, because my x axis and y axis here are the diameter of the ring. So I about the diameter of a ring is equal to half mr square. So you mark, I have mr square, 2 mr square is the axis passing like this, and if it is on the plane of the lamina, then any axis you take passing through its center will be half mr square. So this is how we apply the perpendicular axis theorem. So for the different cases, now I have found out for a ring, for a disc, etc., it is a simple integration. Go through the integration, formula is same, r square dm integration. So a ring I have told you already. For the disc, in the case of a disc, the moment of inertia about this axis, the axis perpendicular to its plane. See, from the diagram, you should say z dash is perpendicular to plane of disc. In all these cases I will be taking that. So and its mass is m. So if the mass of this disc is m, about this axis the moment of inertia is half mr square. Then what will be its moment of inertia about this axis? Using the parallel axis theorem, I will have to add whatever is the moment of inertia about this axis plus mass into this square, this distance separation square. Distance separation is r. So half mr square mu mr square add karibi. So this is half mr square plus mr square. This is by parallel axis theorem. So this will be equal to 1.5. So 3 by 2 mr square. If I use the perpendicular axis theorem for a disc, moment of inertia I want to find out about any diameter. Let us take two diameters which are perpendicular. Two diameters, if I take any two diameters which are perpendicular, x and y, and I know the moment of inertia about z dash. This is half mr square. So Ix and Iy are equal to each other. If you apply the perpendicular axis theorem the way I applied for the ring, it will be half of that, because this moment of inertia about this axis half mr square is equal to this plus this ix plus iy, both are equal 2ix, तामाने ix will be half of that, तामाने यार half, तामाने about this axis it will be 1 by 4 mr square, even any diameter एपटे भी सेया. Now if I take another axis parallel to this axis touching this, lying on the plane of the disc, this line is lying on plane of disc, this a dash. Now एठी ए लाइन पाई जेति की ता संगरे ऐड करिबा mr square mass into the separation एठी r, ता माने 1 by 4 mr square plus mr square. Again I am applying the parallel axis theorem. So this will be 5 by 4 mr square. So when the axis of rotation changes, if the axis of rotation is passing through the center perpendicular to the disc, it is half mr square. Passing through the tangential to the axis parallel to this original axis, then it is 3 by 2 mr square. If the axis lies on the diameter of the disc, it is 1 by 4 mr square, and if it is tangential lying on the plane of the disc, then it is 5 by 4 mr square. Then I will take the case of sphere. If the sphere is spherical, is solid sphere. Now for a solid sphere, any axis is same, is symmetrical. If you take any axis, all these axes passes through the sphere. For a solid sphere, if this is the axis of rotation, then the moment of inertia is 2 by 5 mr square. So let me write it here, I equals to 2 by 5 mr square. Now you can calculate the moment of inertia about this axis. This is axis parallel. So या पाई जेति की plus your mr square, तामाने 2 by 5 plus 1, so 7 by 5. So it will be 7 by 5 mr square. About this axis, the moment of inertia will be 7 by 5 mr square. Now for a, this is case of solid sphere. If it is a thin shell, that means 3 dimensional ring टा होतला 2 dimensional, एटा बर्तन 3 dimensional पतला खाली अछि, बाहरे अछि खाली, चोपाटा खाली बाहरे अछि, बाबा भीतर किछि नाही, and its mass is same m. Then the moment of inertia through the center, again it is a 3 dimensional body, ता पई किछि नाही perpendicular to its plane बोली किछि नाही, a plane हेइ पारे से plane हेइ पारे, so it is the same axis. This is 2 by 3 mr square. You can yourself find out what will be moment of inertia about this. Will be mr square आउ add कर दबा 2 by 3 mr square plus mr square. So this will be 5 by 3 mr square. Now for a rod, in the case of a rod, that means when I say rod means its cross section is very small. So moment of inertia about an axis perpendicular to its plane and passing through its center. If z dash is passing through the center of this rod and perpendicular to its length, then it is m l square by 12. Then tell me what will be the moment of inertia about this axis which touches the end. So here my AB is touching this one end of the rod. तामाने मु एतिके m into a separation रो square टा add करिवि. So this will be ml square by 12. A center रे moment of inertia जहा होतला, this was the moment of inertia about z dash जहा होतला सेतिकी plus mass into separation रो square. The separation here is, if total length is L, this separation is L by 2. So L by 2 ro square. So this comes out to be ml square by 4. So 3 ml square by 3 है जीवो. So it becomes ml square by 3. So for different axis, when the axis is this, the moment of inertia is this. When the axis is z z dash, it is ml square by 12. Then I am left with the case of a cylinder. Like this, right circular cylinder. The moment of inertia about this axis, if z z dash is like this, its own axis, passing through its axis, then this is simply m l square by 12. About this axis, it is m l square by 12. But if you change the axis for a cylinder, if you change the axis to this, passing through its center, cutting the 2 into 2 halves, then it will be equal to m l square by 12 plus m r square by 4. R is the radius, L is the length. This length is L and this is the center, it passes through the center. Then it is m l square by 12 plus m r square by 4. So, these are the formulas which you can find out if you take the integration of r square dm over the entire body. So, in case of, for example, in the case of disc, you divide the disc into small rings. If I consider that this disc consists of several rings of varying radius, if this is the radius at a distance x, thickness is dx, this area of this is the length of this. If I take this ring, imagine this ring, cut it at one point and straight it, means this perimeter of that thing, I will get a strip of this whose thickness is dx, this is the dx, ମୁଁ ଏଇଠୁ काटी देइछि आ ए रिंग टा को सीधा कर देइछि. So, and this length will be 2 pi x, the circumference. So, the area of this one area will be 2 pi x dx. So, if this mass of this thing is, total mass is m, mass per unit area will be mass by, now area of this disc is pi r square. So, this is the mass per unit length into mass per unit area, and the area of this ring is 2 pi x dx. So, this is my mass of this small ring whose thickness is dx and which is placed at whose radius is x. So, this is dm. So, this equals to pi कटिगला 2 m by r square x dx. Now, moment of inertia formula कौन? Moment of inertia है r square dm. r माने distance रो square, केते distance रो अच्छी x रे अच्छी, तेणु एठी हबो x square into dm. dm केते ना 2 m by r square x dx integrated from 0 to r. So, this is 2 m by r square टा constant मु बाहर को नहीं आसली, x square into x है x cube by 3, x cube by 3 को 0 और r कले आसीबो r cube by 3. मास पर यूनिट एरिया नहीं गली मु 2 m by r square x cube by x square x cube dx. This is an integration of x cube dx, not x square dx, 0 to r. So, this will be x to the power 4 by 4. So, this will be 2 m by r square into x to the power 4 by 4 from 0 to r. So, this gives us 2 m by r square or let me write it here, 2m by r square, r to the power 4 by 4, and you get r square cancel out, 2 by 4. So, half m r square. So, the moment of inertia of a disc about an axis, which axis? Passing through its center and perpendicular to its plane will be equal to half m r square, where r is its radius, m is its mass. So, thank you. Next time we will talk about torque and all.